Welcome to the video tutorial on interrupted time series. This is the third part of a three-part series that illustrates how to evaluate retained data using interrupted time series. In the first part of this video tutorial, we review the interrupted time series analysis, steps needed when using this method, and prepared routine data for analysis. The second part focuses on the single group interrupted time series, and in this part, we will focus on the multiple group interrupted time series. In the multiple group interrupted time series, we have one or more control groups available for comparison to our exposed or treatment group. Adding this comparable control group strengthens our approach because it allows us to control for pre-trends and pre-slopes. And one of the key assumptions that we make in using the multiple group interrupted time series is that the confounding emitter variables affect both the treatment and the control group similarly. So as we see in the diagram on our slide, the ITS requires two segments, one before the intervention and one after the intervention. Our X is our intervention or program or policy or interruption. And as the diagram indicates, a minimum of 8 time points are needed before and after the policy in the treatment group. The policy, the interruption, the intervention, and the treatment group. The unexposed group does not have an interruption, but should have the same number of points as the treatment group. As we previously mentioned, ITS analysis uses regression-based technique. In our single group ITS, we didn't have a comparison group, and this was our regression equation. Our T was our time since the start of the study, X a dummy variable indicating our pre and post periods, XT was a time since the start of the interruption or policy or intervention. The multiple group ITS regression built upon the single group ITS equation or regression, and then it's expanded to include 4 additional terms. We now have a dummy variable indicating the type of cohort and several interaction terms. Taking a closer look at the regression equation. So in our equation, our Y is our aggregated outcome measured at each time point. Our T is a time since the start of the intervention or interruption or policy. Our X is a dummy variable representing the intervention period. So pre-intervention periods are 0, post-intervention periods are 1. Our Z is a dummy variable denoting the cohort assignment, where treatment is 1 and control is 0. Our epsilon is the error term. And we have 4 interaction terms, ZT, ZX, ZXT, and XT. And we'll go over these interaction terms in more detail in a couple of slides down. But we also have 8 coefficients in our equation. Beta naught to beta 3 represents our coefficients for our control groups. And the last 4, beta 4 to beta 7, represent values for our treatment group. And using the graphical representation, we'll go through what the different coefficients mean. In our graph, the orange line is the control group and the green line is the treatment group. So our beta naught, which is here, is the controls group existing level or intercept of the outcome. Our beta 1 is the controls group's slope or trend prior to the intervention. Our beta 2 is the difference or the change in the level of the outcome that occurs in the period immediately following the introduction of the intervention for the control group. And so it's the immediate effects of the intervention for the control group and provides the level change after the intervention. Our beta 3 is the controls group's slope or trend change, which is basically the difference in the pre and post slopes or trends. Our beta 4 is the difference in the level of intercept of the outcome between the treatment and the controls prior to the intervention. Our beta 5 is a difference in the slope or trend of the outcome variable between the treatment and the controls prior to the intervention. Our beta 6, which is this, is the difference in the treatment and controls groups level of the outcome immediately following the introduction of the intervention. And our beta 7 is the difference between the treatment and controls group in the slope of the outcome after the initiation of the intervention. So this is during the post-intervention or the post-policy or post-interruption period. So this is a sample data set showing the variables needed to complete the interrupted time series. And many of these variables will be created in order to fit the model. Your data set should come with information in the first two columns, which gives you the year or some kind of date variable, as well as a rate or count. The rates are observations or data collected to determine the effect of a policy or program. And in this sample data set, you have 18 observations for each group. So 18 for the exposed and 18 for the unexposed. The remainder of the variables will be created if it hasn't already been done. T, as we said, tells us the time or the number of data points. X is our dummy variable for when the policy or program or intervention occurred, where 0 indicates a pre-period and 1 indicates our post-periods. XT is the time after the intervention. And so all pre-periods will have a value of 0 and will count the number of observations after. Our Z tells us the cohort type. So 1 indicates that it's a treatment or exposed group, and 0 indicates that it's unexposed. And so you notice also that up until XT, the values we have in T, X, and XT are the same in both the exposed and unexposed groups. For any interaction variable with Z, our dummy for cohort, the control group will be assigned a value of 0, and so which we'll notice here. So going forward and looking at our interaction terms with our ZT tells us the time or number of observations since the start of the study. Our ZX is, then this is for the treatment group alone. Our ZX is a dummy variable for pre and post periods for our treatment group. And our ZXT is the time after the intervention or policy for our treatment groups. And so these are the variables that your data set should have. And we're going to go through analyzing this data set using interrupted time series. As a reminder, our data comes from Exile, a fictional country. In November 2017, Exile introduced a policy that eliminated fees at health facilities associated with maternity care services, with the aim of increasing the use of health services and ultimately improving maternal health outcomes. It was piloted in 2 constituencies, Gold Coast number 9 and Gold Coast number 15, and the control group was North Troy number 26. We received health facility data on the number of women who attended their 4th ANC visits from 2017 to 2020. In part 1 of this video, we prepared our data set by aggregating our data to the constituency level, formatting our counts to rates, reshaping our data, and finally formatting our dates to be recognized by data. And so we have 6 variables in our data set as well as 132 observations. We have our ID variable, which is a unique identifier for each constituency. The region variable is the region the constituency is in, the constituency variable. We have a variable representing the number of health facilities in each constituency, as well as a date variable and outcome variable, which is our constituency rates of 4th ANC visits. This is a visual of our sample data set, and it lists most of the variables we just described. So in our example, we want to answer the second research question specifically. What was the impact of the policy on the use of ANC in the intervention constituency compared to the control constituency? And as we mentioned in the previous slide, our policy was implemented in 2017. So our time points before November 2017 are our pre-periods, and our time points after are post-periods. So the steps that we need to complete the interrupted time series should be familiar at this point in time. So the first thing we need to do is to determine the time periods. We need to know the analytic cohort. And from our research question, we know that our intervention group is Gold Coast number 9 and our control group is North Troy number 28. We need to determine the outcome of interest. Again, from our research question, we know it's the use of ANC, specifically the constituency rate of 4th ANC visits. Next, we want to visually inspect our data, looking for wild points, linear trends, and any other data quality issues. You want to perform your preliminary analysis, check for autocorrelation. You want to run your final model, plot your results, and predict the relative and absolute effects. Going to the first step to determining the time points. In doing so, we'll need to identify the cohort pre and post trends, time since the study, started and the time after the policy was implemented, and the letter 3 as it pertains to the treatment group. Our regression equation is going to be useful to do this. So Y is the outcome, which is the rates or observations. The rates are observations or data collected to determine the effect of the policy. Our T tells us the time since the start of the study. So in our example, each month is an observation. So we'll count the number of months starting from January 2017. Our X is our dummy variable representing our pre and post policy periods. Our Z is a dummy variable for our treatment and controls. Next, we have our XT, which is the time after the policy. And all time pre-interventions will have a value of 0 and will count the number of observations after the policy introduction. And not too long ago, we mentioned that for any interaction variable with our dummy for the cohort C, our control groups will be assigned a value of 0. So for the subsequent terms that we're going to look at, our control groups will have values of 0. Our ZT tells us the number of observations or data points since the study started for our treatment group. Our ZX tells us the post and pre periods for the treatment group. Our ZXT is the time after the policy for the treatment group. So we can include the time variable mdate created in the data set to declare our data as time series data. To do this, we'll need to identify the month in the state internal format. And as you may recall in the previous videos, we converted our dates from the state internal formats to the human readable format. And if you want the mdate variable, you'll need to know this data internal format for each time period in order to include it in the command that will be used to run interrupted time series. Alternatively, you can create a time variable that counts the number of observations, and we're going to do this, where each month will be an observation. We're also going to create the period and post time variable. So these first three we've mentioned have been created previously when we did our single group interrupted time series. In the multiple group interrupted time series, we're going to create an additional 4 variables. So the cohort variable, which is Z, the ZT, which we'll call treat time, and TRT for short of treatment. XT, which is going to be, the variable name is going to be our treat period, TRT period. ZXT will be TRT post times, indicating that these variables are for the treatment group. And so this is a visual of what we would like to get. So the first set for value set of observations is for our Gold Coast number 9, which is our treatment group. And then the next set is for our control group, Royal Troy 26. And if you notice, this is very similar to the previous data sets that we saw, where our interaction terms that involve Z have all the, for the North Troy, our control group have values of 0. And that's important to note as we create variables. We're not going to spend too much time over the time period and post time because we did talk about it in part 2 of the video tutorial on interrupted time series. Focusing on these additional variables we're creating for the multiple group interrupted time series. Our cohort variable, to create this, we assign treatment group to the value of 1 and the control group with a value of 0. For our treatment time, we sorted our data and created a variable that counted the number of observations for each constituency. And we then assign all values in the control group a value of 0. For our treat period, we assigned pre-periods a value of 0 and post periods a value of 1. And then we assigned all values in the control group a value of 0. And for a treat post time, we counted the number of observations after the policy introduction. And we also considered the month the policy was introduced as month 0 and assigned 3 periods a value of 0 as well as a control group a value of 0. So after creating all the variables, this was our data set. They're only the first 21 months are listed for both Gold Coast number 9 and North Shore number 26. So we added 7 variables to the 6 we started with. And so now we have 16 variables. Going forward, I want you to keep in mind that November 2017 is the 11th observation or data point in our time variable. Before we can start our interrupted time series analysis, we must first declare the dataset to be time series using the tset command. Because we know our dataset contains multiple constituencies, we included a panel variable in our command. The dataset can be declared using either the end-date or time variables, keeping in mind that if you were to use the end-date variable, you would need to know and use a stata internal form for the subsequent commands for the interrupted time series analysis. So for us going forward, we're going to use time in the declaration of our dataset. Next, you want to conduct a visual inspection of your data. And this step can actually be done before declaring your data set. You want to use the two-way graphs to do this, either the connected line plot or the line plot, and this choice is entirely yours. The commands are fairly similar. For both, you'll need to know your dependent variable and your independent variable, as well as the year your policy or interruption occurred. So in our case, our dependent variable is constituency rate of fourth A&T visits. Our independent variable is time, and our policy occurred in November 2017, which is the 11th time point in the time variable. In our data set, the intervention constituency is Gold Coast, and the ID for that is 20, and the control group's ID is 235. And we're going to use these IDs in the next graph as well as in our ITSA command. So it's important to note these. So we used the connector line plot. We indicated our outcome and time variable as well as the treatment constituency. And we did the exact same thing for our control group, but indicated our control constituencies ID. Next, we indicated when the policy was implemented, and we labeled our graphs as well, including the x-axis, the y-axis, as well as give it a title. These are the results we got. Our blue line represents Gold Coast number 9, and the red represents North Troy 26. From looking at that graph, it looks like the pre-trends between our controller and our treatments are fairly similar, with the exception of this increase that happens in Gold Coast number 9. And also over the period for Gold Coast number 9, the constituency rate remains fairly the same, except that there are some declines that occur at various points. For our Gold Coast, which is our treatment group, we'll notice that there are also some declines and spikes at different points in time. And to fully understand why this is happening, we'll need to take a step back and look into the literature to see what was happening in Excel during these time periods. And this would obviously affect our interpretation of our results when we do that. Similar to the single group interrupted time series, we'll be using the ITSA command developed by Ariel Linden in 2015. The command can be used to control for autocorrelated disturbances and estimate the treatment effect over multiple periods. And so we'll briefly go through what each component needs. So you'll need to know your outcome variable or your dependent variable, and your outcome variable has to be ordered as a time series. The command allows you to weight your data, but we will not be doing this. The treatment period specifies a time period when the intervention begins. You must use values from what you use when you declared your data set. Since it's a multiple group interrupted time series, we omitted the word single, so you don't see it appearing in this command. Our treatment or treat ID specifies the identifier for the single treated cohort, and this value should be in the panel variable used when the dataset was declared. Our control ID specifies the unique identifier for the control ID. And if you omit the control ID, then all the other groups in the data sets that are not your treatment variables will be considered as controls or be used as controls. You can specify your number of flags that will be considered in the autocorrelation structure, and the default is 0. Figure produces a graph similar to what we saw when we talked about the regression equation. And a few slides back, we created the time period, post time, and other variables associated with the dummy variable for the cohorts. So state IT ITSA automatically generates a lot of these commands as part of our outputs. And so the replace component of the command basically replaces it if it's already been run in Stata and these variables are present. in our data set. And you can search for more information and insights into all these components of the ITSA command. Search help ITSA, and it will give you a deeper insight into them. Just a reminder, this is our regression for a multiple group interrupted time series and the graph that we want to produce. We're answering the second research question, the impact of the policy on the use of ANC in Gold Coast compared to North Troy. So in our preliminary model, we specified our outcome, our treatment ID for Gold Coast number 9, our control ID for North Troy 26, our treatment period. We specified a lag of 0 and we assumed no autocorrelation. We requested a graph and asked data to replace the variables that the command created if they had already been created. Once we run our ITSA, we produce the following output. We're going to present it in a tabulation because it's a little bit clearer. Once you get your output, one of the first things you want to look at are the level difference and slope difference on the second and third rows, which are also in the red box on the screen. The baseline level difference as well as the baseline slope difference between Gold Coast 9 and Gold Coast 26 were statistically significant. And so it tells us that our levels and slopes for each of these are not similar. And so given this differential pattern, we should be concerned. Our treatment effect estimates will be biased. So our North Troy 26 may not be the best control group for Gold Coast number 9. Another way, so what we looked at was our p-value. And so p-values for these coefficients should not be statistically significant. Some researchers suggest that the p-value should be greater than 0.1 on both our baseline slope and baseline level. So underscore z and underscore z underscore t should be greater than 0.1. And because ours are significant, they're not that comparable. In an ideal world, we would find another control group or group of controls. However, we want to answer our specific research question, so we're going to proceed with North Troy as our control group. But we're going to keep in mind that the treatment effect is going to be biased because our slope difference and level difference is not comparable. Moving on rows 1, 4, and 5, also highlighted on the screen, our pre-existing or pre-period trend and slope in the control group is decreasing, but this isn't significant, and the level reduced during the post-period, and the post-period slope or trend was positive, meaning there was an overall increase in the rate. Rows 6 and 7 tells us there was a significant increase in the constituency rate after the policy in the treatment group relative to the control group, but the post-period slope was not significant in the treatment group relative to the control group. So this is a graphical representation which we requested in our data command. So as part of our analysis, we want to assess for autocorrelation, which is the degree of similarity between a given time series and a lagged one over successive time intervals. And it occurs in the time series studies when errors associated with a given time period carry over into future time periods. And so when you overestimate 1 year, you're most likely going to overestimate the following year and vice versa, so that when you underestimate 1 year, you may underestimate the following year. So there's a need to assess for autocorrelation to be able to get accurate estimates of standard errors and confidence intervals. So to detect autocorrelation, we're using the Combi-Huizinga test for autocorrelation. It's a post-estimation command, and once you run it and you receive the output, you want to focus on the significance on the right side of the output. And so for each lag, autocorrelation is present when the p-value is less than 0.05. And as shown on the right side of the panel in the highlighted region, autocorrelation is present from 1 to 5, lag 1 to lag 5, but not at any of the higher lag orders. So we will specify lag 5 in our final model to correctly account for autocorrelation. And so now we will go through our final model. The only thing we changed was the number of lags to account for the autocorrelation. So we now have 5 lags indicated as a maximum number of lags. Looking at the tabulation of our outputs, we'll notice that our coefficients remain the same. However, our p-values and confidence intervals change slightly because we accounted for autocorrelation, and we have a more accurate estimate of these two values. The level difference and slope difference remain significant, which is a reminder that node choice number 26 is not the best control group for Gold Coast number 9, and in an ideal world, we would have found another control group, but we want to answer our research question. The pre-existing trend and level change in our control group remains statistically insignificant, and the level change in the treatment relative to the control was still significant, and the trend change in the treatment relative to the control was still insignificant. And so from our output, we can say that there was a statistically significant treatment effect in the first month of the policy. However, the increase observed in the pre-post trend rate of fourth ANC visits compared with the control of 0.0067 per month was not statistically significant. This is a graphical representation. Our interpretation can be also phrased as, after the policy change in Gold Coast number 9, there was a sustained increase in the constituency rate of fourth ANC visits of about 0.29% relative to the change in North Troy 26. There was an increase in trend of about 0.0067% per month afterwards, but this was not significant. Similar to the single group interrupted time series, we can go a step further and predict changes at different time points by calculating the absolute and relative changes. In our example, we want to determine the impact of the policy a year later. To calculate these two, we need to know the fitted value and the counterfactual. Our counterfactual measures what would have happened to the outcome in the absence of the policy, while the fitted value measures what happened to the outcome with the policy. To find the absolute change, you're going to find the difference between your fitted and counterfactual at a specified time period. So in our case, after the first year. And for the relative change, you're taking your absolute change and dividing it by your counterfactual. And we're going to review these formulas in the next couple of slides. Predicting the counterfactual and fitted value, you'll need to use a regression equation, and it helps simplify the entire process. And for this particular slide, we're focusing only on any time-related variable. We know that the policy was implemented in the 11th month since the study started, and we want to know the impact 12 months later. So we're interested in looking at the impact in the 23rd month. We need to know the number of months since the start of the policy. And since we're interested in the impacts of the policy a year later, our XT is 12. For our ZT, which is the time since the start of the study in the treatment group, is going to be similar to what we got for our T. The difference is that our control will have a value of 0. For the number of months since the start of the policy for the treatment group, it will be the same as our XT or our ZXT, and will be the same as our XT, but the values for the control will be 0. And so now we're ready to predict our counterfactual and fitted values at year 1. For the counterfactual, as a reminder, it measures what would have happened to the outcome in the absence of the policy. And so focusing on what happens in the control group during the post-policy period. And so we know it's a post-policy period, so our X is going to be 1. We determined our T and our XT in the previous slide. Our Z is 0 because it's the control group, and our interaction terms ZX, ZT, and ZXT are 0 because we're dealing with the control group. And so once we simplify our equation, our final equations to determine our counterfactual was our beta naught plus 23 times beta 1 plus beta 2 plus 12 times beta 3. And after running this in data, our value was 0.00138 for our counterfactual. And so a similar process was done for our fitted value. The difference is that our Z was equals to 1. And so after all the values were inserted and simplified, we got 0.00657. A year later, our absolute change, which is the difference between our fitted and counterfactual, once we take the values we got from our fitted and counterfactual on the previous slides, our absolute change was 0.005187, and our relative change, which is the absolute divided by the counterfactual, is 3.761. So to interpret it, we would say that in the first year after the policy, the constituency rate of fourth ANC visits was 0.52%, more than would have been expected if the policy was not implemented. And this represents a 376 percentage point increase. So we went over just a few of the capabilities of ITSA, but it can do a whole lot more. It can be run with multiple treatment policy intervention periods, or intervention periods, multiple treatment groups, as well as multiple control groups. You can account for all the correlation in the initial command using the PREAS, but you have to remove the lag and the number of lag specification. It's also important to note that the output for the PREAS is not comparable to the output when you do specify the lags in the command. You can also control for independent variables if you have them. And keep in mind that ITSA is just one of the many ways that you can analyze interrupted time series data. And there are several more approaches that can be used. So when you run your interrupted time series, you want to report a couple of things. The first you definitely want to report is the autocorrelation and at what level. If there are any considerations you took for seasonality and non-stationary data, you want to provide information on the intervention time points and lag points, information on the number of data points in your pre-periods as well as your post-periods, and any co-interventions that may have occurred during the period of interest. And this is where we are going back into literature just to identify what was happening during our study period. You want to provide information on the statistical regression methods and the appropriateness of a linear model when applied, the intervention impact, as well as the absolute and relative changes. It's also helpful to have a graph so people can visualize what happened, and your graph should have clearly defined time points. And lastly, you want to provide information on the number of data points you had before and after your intervention, policy, or interruption, as well as the number of observations per data point, and if you had any data variability. This is the end of part 3 of the Interrupted Time series video tutorial. We have several resources available: a background information sheet on the Interrupted Time series, the presentation used today, as well as the stata.do files and sample data set for parts 2 and 3 of this video tutorial. Thank you very much for your time and your attention. We hope you learned useful tips about interrupted time series and encourage you to use this tool when you analyze your routine data sets, routine data for evaluation and research.